And I'm going to present our collaborative work because we have some project on ICS anomaly detection methods. And we realized that in order to design and compare and test existing ICS anomaly, it means anomaly detection methods for industrial systems, which, in order to introduce the context, this project is practically oriented. So at the end, we really want to have some ICS anomaly detection method that can be deployed in a real-world environment, can be part of some network monitoring system. So for this project, we had to, or we did some literature survey and identify several anomaly detection methods that were designed for ICS. But before we can use it and say, okay, this method is good, we of course need to do some prototypical implementation for us and evaluate it with different data sets and so on. And for this reason, we realized that if we need to create or develop or design more than a few anomaly detection methods, we would need to have some support, because otherwise we would repeating some task again. So for this reason, we decided to create some software library to support the design of anomaly detection methods. And at the end, we realized that it may be useful also for the community. So that's the reason why we try to present it and write it in and write some information about this method in the paper. So the ICS anomaly detection means that we have some industrial system, and what I'm talking is about to detect anomalies from the network communication. So most of the industrial control systems today are big control system that somehow communicates. They use some communication platform. They use their own industrial standard protocols. And the anomaly detection means that we try to look at the network communication and identify whether there are some suspect communication patterns. There are a lot of methods that were recently developed for industrial control systems because they are usually or often they started as a kind of specialization of the method that are known for the IP communication, for detecting anomalies in internet communication. And also there are some methods that try to exploit the specific patterns that you can observe in industrial communication. So there are many methods that are available as an implementation or prototypical implementation, or only described in the research literature. So if we want to select some suitable method and at the end deploy it in some real-world monitoring system, we of course need to know its accuracy, reliability, but also we want to be sure about its robustness. And by robustness, I mean that it also works in a real-world environment. So it's nice that if you have very accurate method, which is 99.9999, but if you have a lot of traffic, even a small inaccuracy may lead that you generate a lot of alerts, and these alerts somehow make the administrator nervous. So it is necessary that we can understand how the method behaves and we can test it by ourselves. And if we find that the method has some, let's say, weak point, we need to come up with some mechanism how to overcome this weak point, maybe by reducing the number of alerts by some other means. Oh, sorry, it was too fast. Okay. If you consider the different types of anomaly detection methods, we can split them or group them into classification-based, which use machine learning algorithms. These are very popular last time, or the methods that are model-based. They may use, for instance, finite automata or probabilistic automata or some other way how to model the system, or possibly with some rules or something like this. Or time series analysis, where these methods try to observe traffic patterns they may compute a total number of packets sent within some interval, or they may analyze some inter-arrival time. And by this, they may check the different intervals in the communication and search for some periodic traffic patterns, compute some trends, and identify some irregular items. So there are different types of anomaly detection methods. And our idea was to prepare or to set up some environment in which we can implement by ourselves the selected methods and to perform some automatic testing and evaluation in order to identify the strong and weak point of these methods, and possibly to create some prototypical implementation that can be used for the product version of these methods in the network monitoring system. So the design of anomaly detection methods consists of roughly these steps. So at the beginning, we need to prepare the data for the method, because as an input, we may consider, for instance, the raw traffic represented as a packets, or maybe some network flows that are captured by network monitoring devices and provided to the anomaly detector, or some other input data that can be collected in the monitored system. So first, we need to do some data preprocessing. Then usually, if we try to design or to optimize some method, we perform some data analysis. This is mostly manual analysis or interactive analysis, where we look at the source data and try to guess what may be the best feature that represents the data, or best set of features that represents the data, or whether there are some observable patterns and so on. After that, we can create a method design and evaluate this method, and this can be somehow set of repeated steps, because after the first evaluation, we may observe that it is not what we expected, so we need to do some modification of the methods, or maybe we need to get some other type of data or extract some other features. And when we are almost happy, we can do some more experiments with the methods. So we would like to have some implementation that we can run again and again with different data sets and test this method, and possibly to feed this method with some real-world data in order to evaluate it in a real-world environment. So this is the motivation for our work, because if you want to do the data analysis, there's a lot of different tools with very nice and rich environments to perform some interactive analysis. You may know tools like Tableau or RapidMiner, or you can use Python with notebooks in order to do some interactive data analysis, even with evaluation, even with very advanced visualization. But the data preprocessing is something that is usually need to be done in some external software tools. And if we are talking about preprocessing of network communication, we are talking about tools like T-Shark or Scapy, which can be used in scripts to create from the source data some CSV files that can be then consumed in the data analysis part. This is usually done, and what we saw in the literature and also what we experience. So for each case, you try to very quickly set up some basic scripts in order to get your CSV file that can be further analyzed. But if you look back and you see that in different cases, you usually create very similar scripts, then the motivation for our work is how to approach this phase more systematically. So how to create, or whether to create some library that would support this data preparation, and that would easily provide data for some data analysis environments. So this is our motivation. And in this paper, we present the proposal of the library that helps with data preprocessing, and also it integrates with data analysis methods, so that it is not necessary to generate CSV file and then import this CSV file to some other tools, but you can use the output of data preparation phase directly as the input for data analytic part. For analysis of anomaly detection methods, there are usually two work patterns. So the first is interactive pattern. It means that at the beginning you do some mostly manual exploratory data analysis. And then there is the batch pattern when you propose the method and now you want to test it. So to run it several times, so with possibly different parameters in order to evaluate it. And our idea is that we should support both these patterns. So if I work in the interactive manner, I should use the same functions from the library to prepare the data using the same procedure like in the batch pattern. So I can reuse what I did for interactive pattern in later steps for the batch pattern of work. As a data sources, we said that we would like to support raw packet captures. It should be able also to extract prepared CSV files because some data sets that are provided by other researchers are not in the form of raw data, but rather in CSV files. And also because our target monitoring system creates IPFIX records, which are net flow records extended with selected features from the industrial protocols. We would like also to support directly IPFIX records. There are some existing frameworks that, or one of them, traffic identification engine, was the candidate that we first considered to use, but we realized that it was a little bit cumbersome to use it in interactive mode. So the final decision was that we tried to create our own framework for data preprocessing. There are also some other framework. These two are a little bit older and are not currently supported. So we designed a new library for data preprocessing. We choose a .NET framework in core version because it can run on all major operating systems, and the implementation can be done in C# language. This is kind of compromise between Python and C, as these two programming languages are most used for tasks like this. We also analyze MLNet library, which is machine learning library for C# or for .NET Core, and it provides concept of data view. So we use this concept for sharing or to generate the data. So our data, the data that you generate from the data preprocessing, generated as a data view. And by this, it is very easy to integrate it with other data analysis libraries. And there are some major components implemented in our library that performs the data preparation. And this is the entire pipeline that can be used for creating, for training some machine learning models. So at the beginning, we have some, for instance, packet traces. Then in our library, we can apply some packet filters and send these packets to conversation table where the packets are grouped in conversations, which are bidirectional flows. And then we apply on this conversation table either conversation processor or packet processor that just generates the conversation records or packets records that can be directly used as an input to machine learning library, because these conversation records are represented as a data view object, so it can be directly consumed by machine learning. The result of machine learning is some conversation model or packet model that can be used for classification or anomaly detection. I don't have a picture for detection phase, but it will use the same prefix of this pipeline or the start of this pipeline. So again, I generate the conversation records and then I used classifier of this conversation model in order to decide whether the record is okay or whether it is anomaly. So what we have is that we can reuse this first part of pipeline in both in training and in detection phase. So we can be sure that we have the same type of data provided for the for learning and the testing. I already mentioned the data view and these phases, so I can skip it. And this is the example of two relatively small anomaly detectors. And I present this slide in order to show how much line you need to write in order to create this basic detector. So this blue part is implemented using our new library, our proposed library. This purple part is related to using ML.NET for training the classifier and creating the model. So you can see that it's just a couple of lines. The first part in the blue line is data ingestion. It means to loading PCAP files either from interface or a PCAP file, and store it in conversation table. In part two, we apply a processor for Modbus communication that extracts from the Modbus conversations the features that we want to use in the model training. These features like number of readings, number of writings, number of successful operations, and so on. So in this case, we extract some statistical information about each Modbus communication. The second example shows how to implement time series anomaly detection. So we again use the algorithm from ML.NET that performs time series analysis and is able to detect some anomalies. In this data preparation phase, we need to do a little bit different approach. So we just want to analyze all the frames and select only those frames that we want to use in time series anomaly detection, and then provide the things that we use. It means that in this case, we only consider number of frames within some interval, but we can, of course, here extract some other features like the size of the frames and some other things like number of operations and so on. So it depends on this data preparation phase. Sorry, I again use my mouse to move the slides, but I have only 2 slides left. So of course, one thing is that if we can implement this data preparation, we can simplify the process of designing the methods, because we can just write only a few lines in order to prepare data. But we also want to have the implementation that can be comparably fast with the existing approach. So we don't need to wait, although anomaly detection development is kind of offline process. So the performance, I mean, the computation speed is not crucial. Of course, if we can prepare data faster, we can perform more experiments. So we compare it with kind of baseline tools, which is based on T-Shark tool. And this is the comparison on just 3 data sets of different size and different number of buckets. And if we used T-Shark just to generate CSV file that we can use later for analysis, then for instance, for this data set, it took some 15 seconds. So it was for 200,000 buckets. If we use our own approach, and I think that these times are for the example of the anomaly detection method that I presented on the previous slide, then the entire pipeline, it means including training the model, was only 1.6 seconds. So there was also some speed up in terms of computation time that our library provides when you want to design some anomaly detection methods. And it's about 10 times, as you can see, also for other times for bigger data sets. So also in this sense, this library may be quite useful because you can do some things faster, so you can do more experiments in the same time. So our contribution presented in the paper was that we design and create some first version of the software library that can be used for the data preparation and can be combined or integrated with some data analysis methods, and our approach or our focus was on anomaly detection method design. So the library consists of several components that performs data preparation, network data preparation, can extract features from different industrial protocols because we implemented some deep packet inspection in the library, can compose network communication and conversations, can even extract IPFIX records from this communication. So it's a library for preparing data in a suitable format that can be then used by some data analysis libraries. It was implemented in a C# language, so it is expected that these libraries will or can run on .NET Core, which may be a little bit unusual, but as I shortly mentioned, we decided for this language because it's something between Python. It has better performance than Python, and it's relatively easier to write some program, and these programs are shorter than if you write it in C code. We also demonstrated how easy it is to use this preprocessing library and how easy it is to use to integrate it in order to write some simple anomaly detection method. This library is currently publicly available, so this is the GitHub link where you can download source codes of the library. And we already use this library to write and test several anomaly detection methods for industrial systems. But we expect that, of course, when we progress further in our project, the library will be more comprehensive, and we also at some moment need to polish it, provide documentation, and some other things related to the easy to use of this library. So that's all. So thank you for listening to my presentation, and if you have some questions now or maybe for offline discussion.
Yes, maybe just a short question. So this is, if I understood, is like batch processing. Do you plan maybe to make it iterative, like continuous? That would be, I think, very interesting for
actually
systems.
With the support of C# language for notebooks, because originally notebooks were only limited to Python, but now there are other languages supported in notebooks. It is possible, and I have also, and in on GitHub there are also some notebooks where the methods are also developed, and in notebooks you can do the interactive analysis. So you can just perform the interactive data extraction, transformation, then run the analysis.
I think it's important for this continuous operation. Like for in big data nowadays, Spark is something which is used for these purposes. But since you use C#, then yeah.
So
okay, thank you.
Yeah. The goal is also for batch processing, also for interactive processing. We don't plan to create our own user interface for doing this, but we rely on notebooks to perform the interactive data analysis, which is currently one of the standards how to do that.
Okay, thanks.
Okay, thank you for questions. I don't see
any... I have a question.
Okay, yeah, please.
Sorry, or maybe two, if possible. Did you run it on any other platform?
You mean the library running on platform like operating system or something like this? Or?
Yeah, or processors or...
It can be run on any platform that supports .NET Core. So currently it's, except Windows machines, it's for several Linux versions and also on macOS. Actually, I'm working part on macOS and part on
because
Windows.
I'm just wondering, okay, you show good, let's say, numbers against the C#, but I wonder if these numbers, I mean, I don't know exactly the context. Maybe it's enough, or maybe you would like to have more. So that's why I wondered if changing a platform or even run it, let's say, bare metal could bring even more advantages in timing, at least.
Okay.
And then one question, maybe I didn't get it. Slide 11. I was just wondering if it's I only see machine learning trainer. Is this just the training phase, or?
Yeah, this is the picture of training phase, because the testing phase or detection phase will be very similar. It also ends with conversation records represented as data view, but instead of machine learning trainer, there will be conversation model which was created before, and calling the method of this conversation model to detect the anomalies. So yeah, this is only the training phase, but the testing phase or detecting phase will be very, very similar. And actually the data processing part will be exactly the same. And we even combine this data preprocessing part with this in the model. So we modify the model created by MLNet library and create some extended model that includes data preparation. So when you train the model, you know what you use for data preparation, and you use the same procedure, same pipeline for data preparation in order to be consistent in the data.
Yeah, thank you.